So if we look at the do now, these are two multiple choice questions. So number one, consider two samples of gas in identical rigid containers. So rigid container is just something like a glass or a metal container, cannot expand or contract. Gas A is at 273 Kelvin. Gas B is at 300 Kelvin. Which of the following statements are true? So the only thing that we are given in this problem is that they're in identical containers, which means equal volumes. And then we're given the two temperatures. So which of the following statements are true? So it talks about our different options. We have kinetic energy, speed, moles of gas, and then pressure. So if all we are given is temperature, remember that temperature is a measure of average kinetic energy. So remember that temperature is a measure of average kinetic energy. If they're at the same temperature, they have the same average kinetic energy. These gases do not have the same temperature. So the one that has a higher temperature, according to the kinetic molecular theory, that's dealing with gases moving around, the motion of gases. The higher the temperature, the faster the gas particles move. So the more they collide, the more pressure, and then also the more they move, the higher the kinetic energy. So based on temperature and knowing that that has to do with average kinetic energy, which answer is the best choice? Which one talks about kinetic energy? Okay. We're going to talk more about speed next week because speed is only a part of average kinetic energy. Kinetic energy is 1/2 mv squared. So the speed of the gases also has to do with the mass. So if all we are given is information about temperature, then we know about the average kinetic energy. Number 2, decreasing the temperature of a gas from 80 degrees to 40 degrees causes the average kinetic energy to, and then it gives us 4 choices. Now, this is not supposed, well, it is kind of supposed to be a trick question, but this question is really so that we can focus on the temperatures. Whenever you do gas law problems, whether you're using the combined gas law, the ideal gas law, the temperature scale that you have to use is Kelvin. You cannot ever use degrees Celsius. Even if the initial temperature is degrees Celsius and the final temperature is degrees Celsius, you have to use Kelvin because every variable in a gas equation is proportional to the absolute temperature scale, which is Kelvin, because absolute means that it doesn't have negatives. So in order to know how, in this case, average kinetic energy is affected, you have to convert these to Kelvin. Now let's say that you forget how to convert between Celsius and Kelvin. Remember that it is on the equation sheet. So over, there it is, right underneath gases, 1, 2, 3, 4, 5th equation down, under gases, has K equals C plus 273. So if you forget, there it is on the equation sheet. So I'm going to add 273 to both of these. 80 plus 273. So we have 353 Kelvin, 313 Kelvin. This is what we look at when we're looking at how variables will change. Right, so gases are always directly proportional to the Kelvin scale. So if temperature is going down, just in general, if temperature is going down, what should happen to average kinetic energy? Should go down. All right, so I'm going to cross out B and C. Average kinetic energy should go down because temperature is decreasing. Now, Notice how A, it decreases by a factor of 2 because in degrees Celsius, it decreased by a factor of 2. However, when you are comparing variables, you have to compare Kelvin. This is not decreasing by a factor of 2. Decreasing by less than a factor of 2. So, D is our answer. So this do now is all about average kinetic energy. Remember that according to the kinetic molecular theory, so that's when gases are in motion, they're colliding, temperature is a measure of average kinetic energy. If they're at the same temperature, they have the same average kinetic energy. If they're not at the same temperature, like number 1, the higher the temperature, the more motion, the higher the average kinetic energy. Okay, so that's it for the do now. Go ahead and get out your notes packet, a calculator, and your equation sheet, just so that you get used to using your equation sheet. While you guys are getting that out, I'm going to go over some questions that I saw from last night. The biggest question actually came from Avogadro's hypothesis, so I'm going to talk a little bit about that and actually show an example I just screenshot from an old multiple choice question. So, Avogadro's hypothesis. Right now I'm focusing on the conceptual idea of Avogadro's hypothesis. On the next slide I'm going to show you the combined gas law. We'll go through math stuff together, but for now I want to focus on the concepts. Avogadro's hypothesis. You do not need to know the name of any of these laws, any of these hypotheses. You just need to know how to use them, how to apply them. Avogadro's hypothesis says that if you have equal volumes of gases, so you have, in this case, you have 3 containers, they're all equal volume, and the same temperature and pressure. Right, so if you have equal volumes at the same temperature and pressure, you're going to have the same number of molecules or the same number of moles, no matter what the gas is. So in this case over here, we have helium, nitrogen, and methane. 3 completely different gases. They have different molar masses. That doesn't matter. If they're at the same volume, pressure, and temperature, they have to have the same number of molecules or moles of a gas. This we'll kind of talk about a little bit more tomorrow when we look at the ideal gas law, because that's PV equals nRT. So if P, V, and T are all equal, N must also be equal. And so here it shows they're all equal volumes, equal pressures, equal temperatures. Even though the molar masses are different, they all have the same number of molecules. They're all at 1 mole. Over here, there's hydrogen, oxygen, and CO2. Again, they're all at the same volume, same size balloon. If they're at the same pressure and temperature, they're going to have the same number of molecules. That is just what Avogadro's hypothesis states. This actually relates to the ideal gas law. So we will relate a lot of this to the ideal gas law tomorrow and Thursday. So now as we get into some of the math, like I said, you do not need to know Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law. You do not need to know the names of them. Honestly, you don't even need to know each of those individual formulas. If you know the combined gas law, you could solve everything. So if there is one equation that you memorize, right, you have to memorize the combined gas law because if you look on your equation sheet, it's not there. So if you memorize the combined gas law, we can solve everything. So when we combined all of the gas laws, we actually got P1V1 over N1T1, but typically the moles of gas are constant. So that's actually how we get the combined gas law. That's just P1V1 over T1 equals P2V2 over T2. In terms of the relationships, P and V are inversely related. So that means as one goes up, the other has to go down. Which even without memorizing all of these like direct and inverse relationships, just think about that simulation from yesterday. And if you want to go in and you want to, play around with that simulation, it's linked in the lesson plans and it's linked on the slide from yesterday. But think about, if you increase volume, you're decreasing the number of collisions and that decreases pressure. So as volume goes up, pressure goes down. Everything else is directly related except for N and T, but we don't look at just moles and temperature on its own. Moles and temperature usually get tied into everything else. But pressure and volume, in terms of the combined gas law, are the only inversely related variables. Everything else is directly related. As we use the combined gas law, so before I put the first example up here, it's extremely important to remember, as long as your units match up, you don't have to convert pressure to ATM. You don't have to convert volume to liters. However, you do have to convert temperature. The only variable that you have to make sure that you convert is temperature. So if we look at the two examples, so examples 1 and 2 are on page 4 in the notes. So in the notes packet at the bottom of page 4 are where we'll find these two examples. So obviously today we're talking about the combined gas law, so we know that's what we're going to be using. But I'm going to try to talk through these examples because as we start getting into the ideal gas law and Dalton's law of partial pressures, we have a lot of different formulas, different ways to solve problems. And so I want to make sure that as we look at some of these problems, we know how to tell that we're using the combined gas law. So this is the gas pressure in an aerosol can is 1.5 ATM. All right, so that's a pressure. I'm just going to label it P for now. At 25 degrees Celsius, right, there's a temperature. What is the pressure? So it's asking for a new pressure when the can is heated to 450 degrees Celsius. Now what I notice by labeling these variables is that I have two pressures and two temperatures. Which means if I have two different sets of conditions, that's the combined gas law. So I'm going to label these. 1.5 ATM goes with 25 degrees Celsius. So I'm going to label that P1 and T1. This new pressure that I'm solving for, I'll label P2. 450 degrees Celsius, I will label T2. It's important to make sure that you remember that you have to put the variables that belong together. So if I write out the combined gas law, P1 V1 over T1 equals P2 V2 over T2. This is the only gas law out of all of these simple gas laws. This is the only one you need to memorize. Now, the problem says nothing about volume. So we assume volume stays constant. So I'm just going to cross out V1 and V2 because we assume that they stay constant. Before I plug any variables in, if you are given temperature, make sure it is in Kelvin before you even plug it in. Temperature has to be in Kelvin. You need absolute temperature. So add 273. So it's 298 Kelvin and 723 Kelvin. Temperatures have to be in Kelvin. So then I'll plug everything in. So 1.5 ATM is P1. 298 Kelvin is T1. I'm solving for P2. 723 Kelvin is T2. So when you have any of these equations that are derived from the combined gas law, these are proportions, so we cross multiply. How could you solve it differently? Yeah, you could. Typically, the easiest way is to cross multiply. So 1.5 times 723, 1084.5 plus 298 times P2. So then when I divide by 298, 3.64 is what I get for P2. It's going to be in the same unit that P1 was in. So 3.64 ATM. You use the combined gas law every single time. Just cross out whatever's constant. If it's not mentioned, it's constant. And then we can just ask ourselves, okay, so if temperature went way up, does it make sense that our pressure went up? Yeah. Because as you increase temperature, you're increasing the motion of the particles, you're increasing the number of collisions, so it makes sense that pressure also went up. Right? And it went up, a little more than twice, like a little more than doubled in terms of the absolute temperature, from about 300 to just over 700. So it just more than doubled, and if you look at our pressure, it just more than doubled. Okay, so that's example 1. We have one more that we'll look at with example 2. So now, with example 2, they're giving us a lot of information in this problem, so it always helps to go through and to label everything. Label your pressures, your volumes, your temperatures. So for this, an inflated balloon has a volume of 6 liters. All right? So, volume. At sea level, which is 1 atm, so there's a pressure. It's allowed to ascend until the pressure is 0.45 atm. There's another pressure. During ascent, temperature of the gas falls from 22 degrees Celsius to negative 21. Temperatures. Calculate the volume of the balloon at its final altitude. So when I label all of these variables, I notice I have 2 pressures, 2 temperatures, 2 volumes. When you have 2 sets of conditions, that tells us that we're going to use the combined gas law. So before we can use the combined gas law, right, P1, V1 over T1, P2, V2 over T2, we need to know all of the variables that go together. So we need to make sure that we're labeling the first set of conditions and the second set of conditions. So if I have a volume of 6 liters, I'll label that V1. So I need to find all of the conditions that go with the initial volume. Well, we have this initial pressure, and then the initial temperature of 22 degrees Celsius goes with the initial volume and initial pressure. So this 0.45 atm, that's the final pressure. Negative 21 degrees Celsius is the final temperature, and we're solving for that final volume. So it just helps if we label everything. Then as we get into the ideal gas law, we can tell the difference because we only have 1 set of conditions versus 2. So now I'll plug everything in, except I need to make sure that my temperatures get converted. You cannot ever plug in degrees Celsius. That's one of the most missed things on using the combined gas law. It's not the math, it's not solving, it's making sure that you convert to Kelvin. Because Kelvin does not have negative numbers. That's why we use Kelvin. It's the absolute temperature scale, no negatives. You can't have a negative pressure, a negative volume. So then we can plug everything in. So P1 is 1 atm, V1, 6 liters, T1, 295 Kelvin. T2, 0.45. B2 we're solving for. T2, 252. Now the way that you solve this is up to you, whether you cross multiply or you just kind of solve on each side. I'll cross multiply. So 6 times 252. I'm writing down extra work just so you guys can see how I'm getting the answers. 295 times 0.45. So 1,512 divided by 132.75 gives us a volume of 11.4. What should be the unit for the volume? Liters. Right? It's going to match the initial volume. And so with this might be a little bit harder to check our work to see, does 11.4 liters make sense? Volume went up. This might be a little bit more difficult because we have two different things happening that will affect volume in different ways. So we have pressure going from 1 atm to 0.45 atm. So pressure is going down. When pressure goes down, that means that we're reducing the number of collisions. When pressure goes down, volume will actually go up. Those are the inversely related. So based on pressure, we expect volume to go up. But then if we actually look at temperature goes down, we would expect volume to go down. So actually looking at this, sometimes there are questions that say, which variable has more of an effect? Well, if our volume went up overall, pressure actually has more of an effect on this.